Hello my dear students, welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today we are going to study the topic Pauli-exclusion Principle. This principle states that two electrons in any atom will never have same set of all four quantum numbers. So let me write this thing. Pauli-exclusion Principle states that two electrons in any atom will never have same set of all four quantum numbers. So now let's analyze different cases of address of the two electrons. Before doing that, let us recapitulate one thing. We were having four quantum numbers. The first one is principal quantum number. It is denoted by small n and it signifies the shell in which electron is present. The second one is azimuthal quantum number and it signifies the subshell in main shell in which electron is present. The next one is magnetic quantum number. It signifies the orbital in subshell in which electron is present. And finally we are having spin quantum number and it signifies the spin of the electron in the orbital in which the electron is present. The spin of electron can be clockwise. So the clockwise spin of any electron is represented by +1/2 value of spin quantum number, and other is anti-clockwise spin, which is signified by -1/2 value of spin quantum number. So now let's take different cases. I'm talking about firstly case number 1. Let us prove Pauli-exclusion principle. Now case number 1 is when two electrons are present in different shells. Case number 1 is when two electrons are present in different shells. Now the shell is represented by principal quantum number n, so n will be different for both the electrons. Now the azimuthal quantum number is represented by small l. The small l can be same or it can be different. Now let's talk about the magnetic quantum number small m. This can be same or it can be different. And let's talk about the spin quantum number small s. That can be same or it can be different. for the two electrons when they are present in different shell. The principal quantum number will always be different for this type of case. So now let's talk about the case number 2. Now I'm talking about case number 2. When the two electrons are in same shell but in different subshell. Now I'm writing when two electrons are in same shell but in different subshells. But in different subshells. So in this case, the two electrons are in the same shell. That means the principal quantum number n will be same for both the electrons. Now let's talk about the azimuthal quantum number L, which signifies the subshell. So the electrons are present in different subshell. So L will be 100% different for both of the electrons. Now let's talk about the magnetic quantum number small m. The small m can be same or it can be different. Now let's talk about the spin quantum number. Again, the spin quantum number can be same or it can be different. But we are dead sure about principal quantum number, which will be same, and azimuthal quantum number, which will be different. Now let's talk about the case number 3. Here it comes out to be case number 3. When the two electrons are in same shell, in same subshell also, but in different orbitals. I'm writing when two electrons are in same shell in same subshell but in different orbitals. In that case, the electron is firstly in the same shell, due to which the principal quantum number n will be same for both of the electrons. Now let's talk about the azimuthal quantum number, which represents the subshell. Here the two electrons are in the same subshell also, so azimuthal quantum number will be same for both of the electrons, but they are in different orbitals. Magnetic quantum number specifies the orbitals, so electrons are in different orbitals, so magnetic quantum number will be surely different. However, the spin quantum number, it can be same or it can be different. So now let's talk about the last case, the case number 4. When the two electrons are in same shell, in same subshell, in same orbital, but with opposite spin. So I'm writing case number 4. When two electrons are in same shell, in same subshell, even in same orbital also, but with opposite spin. One is clockwise, another one is anti-clockwise. Here I'm writing but with opposite spin. So here what will happen? The electrons are in same shell. The principal quantum number will remain same for both electrons. They are in same subshell. So the azimuthal quantum number which specifies the subshells will also remain same. They are in same orbitals. So the magnetic quantum number which represents the orbitals will also remain same. But they are with opposite spin, then surely the spin quantum number will surely be different for both of them. The electron with clockwise spin will have plus 1 by 2 and the electron with anti-clockwise spin will have minus 1 by 2 value of spin quantum number. Let's take an example of case number 4. As this one is important, it will give you clarity. So I am taking example of case number 4. For example, I am taking 2 electrons, 3d2 and 3d7. Firstly, we know that we are talking about here about the d subshell, and we know that in d subshell we have 5 degenerate orbitals. That is the orbitals with equal energies. So I am drawing the 5 orbitals in the box form. First, second, third, fourth, and a fifth. So these are the 5 orbitals. So now let's talk about 3d2 first. For the case of 3d2, firstly the principal quantum number will be 3 because it's a third shell. That's why principal quantum number will be 3. Now let's talk about the value of L. For the value of L, we are having 4 values, 0, 1, 2, 3. The 0 value specifies S, 1 specifies P, 2 specifies D, and 3 specifies F. Here we are having D subshell. For D subshell, my L will be 2. Now let's talk about M. What's the value of M? It's minus L2 plus L. Please come back to the degenerate orbitals. The value of M will be minus L2 plus L. So this is minus 2, minus 1, 0, plus 1, and the plus 2. So here we are talking about 3d2. 3d2 stands for we are talking about the second electron of 3d subshell. So come back to degenerate orbital. We are going to fill these 5 orbitals according to the Hund's rule, which we have done in the previous lecture, and which states that all the degenerate orbitals gets 1 electron each. After that, pairing will start. So now let's apply that. Here comes the first electron in minus 2. Here comes the second electron in minus 1. So we got the second electron in minus 1. So the value of M comes out to be minus 1. Now let's talk about the S, the spin quantum number. The second electron is of clockwise spin in the minus 1 number orbital. It's a clockwise spin, so the value of S will be plus 1 by 2. So these are the 4 quantum numbers of 3d2, the second electron of 3d subshell. So now let's talk about the 7th electron of 3d subshell. So now let's talk about 7th electron of 3d subshell. I'm talking about this thing. Here, what's the value of N? It will remain 3 because it's the third shell. Now let's talk about the L. It's 3d. For d subshell, we have the value of L to be 2. So we got the L to be 2. Now let's talk about the M over here. For M, we have filled 2 electrons. Let's come back to the degenerate orbitals. Now here you can see that we have filled the 2 electrons. Now here's turns comes out to be third electron. This is a turn of third electron. So it's the third electron. Now the fourth electron. Now the fifth electron. So according to Hund's rule, All the 5 orbitals have got 1 electron each. Now pairing will start from 6th electron. So here comes the 6th electron and here comes the 7th electron. Now the 7th electron is in -1 number of magnetic counter number. So again m comes out to be -1. Now let's talk about the spin quantum number. Here the 7th electron is of anti-clockwise spin in -1 magnetic quantum number. It's of anti-clockwise spin, so S will be -1 by 2. So we got the case number 4, in which you can observe that the quantum numbers of both the electron, the 2nd electron and the 7th electron. Here n is same for both, L is also same, and magnetic quantum number m is also same, but they have a different spins. The first electron in the orbital has a plus half spin because the clockwise spin, so we can take the value of s to be +1 by 2, and the another electron of that orbital will be of -1 by 2 spin. So here we got the spin of 2nd electron in 3D subshell to be +1 by 2, and the spin of 7th electron in 3D subshell comes out to be -1 by 2. So this is the example. Hopefully you got this. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please like, subscribe and share my channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.